right. Good morning, everyone. Great to see so many people here, and glad to be starting off first thing in the morning. So today I'm going to be talking about using open source to address regulatory requirements. And the focus of this is software orchestration because it is a complex topic that goes across some complex domains. So that's what I'm going to try to summarize and give a perspective. And to be clear, this is from a commercial vehicle perspective. So I know a lot of people have passenger car-centric backgrounds. So I'm going to explain the differences and why we're tackling this as one of our biggest priorities. So to start off, to tell you a little bit about Cummins, my employer, we are a $34 billion company, 72,000 employees, and we have operations in 52 different companies globally. We make internal combustion engines, mostly known for diesel, but also hydrogen and natural gas internal combustion engines. We make hydrogen fuel cells and also battery electric powertrains as well, and provide all of those across not just trucking, but also industrial and mining type applications, as you can see here. And we were an early adopter of telematics, the industry was. So in 1990, we actually owned a telematics company to bring connectivity to our vehicles because it was of such value to fleets. We work with hundreds of OEM partners. So that's going to be a theme because with so many different partners, we can't have a bespoke solution for every different implementation. So you think of our embedded ECU software to come up with 100 different variations of that, especially when it's emission certified component, it's very difficult to do. Versus passenger car, our volumes are a lot lower, and our primary driver is the return on investment of the fleet. Can we reduce operating cost? Can we reduce fuel consumption? Can we reduce downtime? If we can affect cost, we can implement a technology. If it negatively affects cost, there's no interest at all from the fleets. And finally, as I mentioned, there's a lot higher variation and lower scale. So if you look at one particular vehicle from one truck OEM, it may have 3 different engine displacement options from 2 or 3 different engine suppliers. So it is that level of customization that the commercial fleets want to optimize the vehicle for their usage. So with that, we started what we call our Open Telematics Initiative, and that is to have open source and open standards collaboration with OEM partners to reduce cost and drive adoption. So the first key aspect is fully portable applications. We can't be writing our Edge or HPC applications over and over for each OEM partner. The second is we need a way to update those applications and to keep them current. The third is we need to standardize the interfaces and make those interfaces secure. So even if the application itself is portable, we also need the API and the interface to also be portable in addition to that. And then longer term, what we want to build on top of this infrastructure is a service-oriented architecture. So why did we choose regulatory requirements and software update as the reason for this? And really, what is even the problem that makes this so difficult? Well, first of all, one is emissions. And what may not be obvious, but as a commercial vehicle powertrain provider with all the modularity and variation, the Tier 1 is responsible for certifying the powertrain for most commercial vehicle applications. So we are responsible for the emission certification and any penalties that happen with that. And we know on the horizon there is in-use emissions reporting. In fact, in China, with our joint venture engines that we produce there, we've had mandatory in-use emissions reporting since I think 2018 or 2019. And there's also the potential for forced software updates. So if something goes out of compliance or we identify an issue, there could be daily penalties until that software is updated. So the Tier 1 has very high incentives to keep the software up to date, especially if it's an emissions-related component. But on the other side, I think a lot of people are familiar with the UN regulations 155 and 156. This is around software version tracking. There's an optional component there around doing software updates. And what's interesting here is the OEM is responsible for compliance here, and really the Tier 1 has no responsibility from the regulatory standpoint. Obviously, they can certify their solution with the OEM, but the OEM is ultimately responsible. So this brings about the problem statement. From the Tier 1 side, we have to meet emissions regulation regardless of what the OEM's doing for connectivity or anything else. This is expensive to implement, so we can't tailor every one of our ECUs to meet every OEM's update solution that they may have, because it becomes very difficult to certify, especially an emissions critical component like the ECU software is itself. But from the OEM perspective, must meet UN regulations, responsible for system level validation. They don't want a Tier 1 software update to somehow cause an issue inside the vehicle. And from their perspective, they can't easily integrate 10 different Tier 1 software update mechanisms into what they have into production today. So it becomes a very difficult and expensive integration exercise for the OEM to solve this problem. So what our proposal is to integrate Tier 1 software update mechanisms into an OEM-controlled vehicle software update manager and develop a methodology for doing that. So why is this a great use case for open source? Well, first of all, it's driven by regulations. Nothing drives adoption like regulations. The second is it's great for open source. This isn't really a differentiating feature. There's no one who's going to gain market share by having a compliant OTA update solution. It's something that must be in place. Third, there's a lot of variation, which means there's a benefit for standardization. And that also drives a great business case, because cost reduction is very apparent when you look at the complexity of the solutions and the variations of the solutions. So standardization can show cost reductions. So I wanted to give a little bit of background on how we got to the place we are today in the commercial vehicle industry with software updates. So starting in 2015, we rolled out over-the-air updates for our vehicles using aftermarket telematics providers. We actually partnered with 35 different third-party telematics solution providers. They installed their hardware in commercial vehicles, and we worked with them to implement our update mechanism. During that time, OEMs started to add telematics capabilities, but they weren't really feature complete or competitive with aftermarket. So that's how it's been over the past 10 years. Well, the big change in 2024 is the aftermarket hardware, for the large part, is going away, and it's being replaced by our own high-performance compute that is designed to do edge analytics and software update of the engine itself. The key feature is it's mounted on the engine, so it is part of the equipment that we sell to OEMs, and it doesn't have a cellular connection, so it integrates with the OEM device to some extent to deliver connectivity. But really, that's not the ultimate solution we want, because we basically have two high-performance compute units doing the same thing. So we need software architecture to allow us to combine those, and that's really what we're focusing on for the next generation after 2024, where you see the OEM has high-performance compute, and then our applications become a tenant on the OEM's device. Now, this is great, like, in concept of how it works, but actually, to get the interoperability, hardware abstraction, API abstraction, that requires a lot of effort, and that's what we're going to be talking about over the next few slides. So the most difficult problem to solve is, how does software become interoperable across all of the domains? This is the work from last year from the software orchestration blueprint. And you can see, we had the cloud domain, the vehicle domain, and on the right-hand side of the page here, you can see we had a lot of different update mechanisms, and then we had some update clients on the left. So this was great for proving out a proof of concept of something that would work, but the issue was there's no real way to scale this to the wide variation of solutions that are in production today. So let me give an example of what those are. So starting out with the domains, we have a cloud orchestrator. And below that, there's a cellular connection down to the vehicle. After that, we have the high-performance compute and its own vehicle orchestrator. Now that needs to transverse CAN and make it to the legacy ECUs to do updates there. So let me talk just a little bit about the variation we see across these, and this is a high-level summary of what that would be. For the cloud orchestrator itself, just in Eclipse, we have the Symphony project, but there's also proprietary orchestrators that are much more prevalent in production by all of our OEM partners. And I showed 2 here. I think the realistic number is probably more like 10 to 15 different cloud orchestrators in use by our different OEM partners. Next, if we go down to the HPC orchestrator, we have 3 different Eclipse projects, all performing generally the similar tasks. There's the Kanto Update Manager, Eclipse Blue Chi, Eclipse and Kaios, and then numerous proprietary edge orchestrators as well. And then finally, we can move down to the embedded ECUs. And here really, even if ECUs all use the UDS standard, they implement it differently. The diagnostic sequences are different, the security is different, and the protocol and update sequences are different. And then many ECUs don't even use UDS. They'll use their own proprietary messages over CAN. So again, it's a very complex and distributed and not easy to solve type of problem, especially when you want to update each one. So to summarize the problem, huge variation across the industry of the different solutions, huge variation across all the domains that we saw, cloud, in-vehicle, and CAN itself. There's no clear leader to reference as a de facto standard. So we thought, oh, do we take Kanto or Blue Chi and have that API be the reference point? Well, that didn't really make sense because everyone else would arbitrarily have to change. And came up with the idea that we really need a next generation type architecture to solve this. It's not going to be solved the way the existing applications have been implemented. So now get on to the interesting part of identifying the solution and how we've solved each one of these layers. So again, we have the cellular boundary and the CAN boundary, and try to figure out how to implement something that can standardize interfaces and solve a common problem across all of these. So again, we have the cloud orchestrator, the vehicle orchestrator, and the different ECUs along the bottom. And as I said, it's really standardizing the boundaries and the interfaces that can help create a longer-term solution. So the first, cloud to vehicle. It shouldn't be an API because APIs can be arbitrary. What we're looking to do is to create a software update U-service. I'm sure you're familiar with U-protocol and U-service, and if not, there's a talk tomorrow to have more information on that. But we're looking for a U-service to define how to do software updates, deliver the software payload, check all the statuses, and initiate all the sequences for a software update. The second big issue to address is the vehicle software orchestrator has to communicate with numerous different ECUs that all have different interface standards. So the way we accomplish that is to extend the U-service a layer below from the vehicle orchestrator down to an orchestrator agent. And each agent can be specific to each ECU. So again, it takes the same standard and it extends it down one more layer, and it allows these smaller plugins that have ECU-specific functionality, but it abstracts all those proprietary functions away from anything above it. So it looks like a simple standard integration regardless of how the ECU is built or what communication standard it uses. Now we get to the next problem that needs to be solved. We have these agents, they all need access to CAN, but every telematics device has a different methodology for accessing CAN, different APIs, and a different CAN stack. So we don't really want to get into the situation of having to rewrite every agent for every OEM implementation. So that's where Eclipse Cannot comes in. So Cannot, it is an abstraction layer for CAN. So everything becomes a just a standard API and a single implementation. And then it takes care of the CAN stack and the CAN library. And traditionally, CAN is either a yes/no. The application has access or it doesn't. Well, we're adding a security manager or an access manager inside of Cannot as well, which can do granular application-specific restrictions of what's allowed on CAN. So we know from an OEM perspective, they just don't want 20 different applications running on the high-performance compute that all can do anything on CAN with full access. So what it does is, the orchestrator agent 1 is restricted to only being able to access ECU1, only with the UDS protocol, and only with a certain bandwidth, and perhaps even only scheduling it at a certain time when there's a software update in place. If there's no software update, turn off the CAN access. So, talk a little bit more about cannot. This is something that we talked about contributing at EclipseCon last year. Well, happy to say the code has been contributed. We do have all the source code available for all these components. And a lot of it is production intent. So not only production intent, but it is in production as of last month. So the way this works, and I'll point out that this covers all the 4 things we were hoping to accomplish with the Open Telematics initiative. So if we start at the top, you can see there are applications. This can be the client updater. This could be the master vehicle orchestrator. It could really solve any of these functions, but the applications become fully portable because they're in an OCI container. And for any of these applications that need access to CAN, all they need to do is to integrate the CAN client into their library, into their application. And once that's done, it handles CAN's communication of everything down below. So it's really kind of transparent what architecture is below that application. What we're using is an MQTT broker to standardize all the signals. Then that goes to the CAN server that consolidates all the client messages. It passes it through a commercial CAN protocol library. So this, unfortunately, cannot be open source because a lot of the protocols, such as SAE J1939, are proprietary and closed source. So we have to have a commercial component that sits in the middle of this. And then finally, down below that, we have the CAN Access Manager, which is the granular security manager that turns on and off access based on each application. And what we're working to implement is security certificate-based authentication. So we have applications IDs today, but we know that those aren't necessarily the most secure, so we're looking to do a certificate-based authentication as well to further secure the access to CAN. And on top of that, obviously, we can build the open software orchestration that I talked about in the previous slides, and that software orchestration can use the service-oriented architecture. So that hits all 4 of the solutions that we needed to solve and we set out to solve 2 years ago. And I will say we've talked to a lot of OEM partners about this and in the commercial vehicle space, and some are completely on board because, yes, we have this problem, we need to solve it. Others are a little reluctant because it's a security change, and having a third-party tier 1 to have a secure session with an ECU, they see that as a potential security problem. Whereas it's kind of different for the tier 1 because we see having a secure session with our ECU as the only secure way to communicate. So that's why it's important to have this stack available and to have the CAN Security Manager to solve both the OEM's problems about too much access and the tier 1's requirements of standardizing that access. So, let's go through a summary of the solution. The software update use service defines a service for updating all types of software in a vehicle. So it can be containerized apps, it can be the operating system on the HPC, it could be infotainment even though we don't really work in that domain, and it can do embedded ECU updates as well. And I will say we are using this containerized approach to update our in-production Acumen device. That is the name for our telematics stack and hardware. We are using pretty much all open source software on that device. It also defines a standard for software version monitoring and updates. So we can use that to identify the version of software that's running in the vehicle. We can set target versions. We can transport the firmware down to the vehicle, and then we can do software update sequences of whatever that may be, of initiating the download to the ECU, moving it from secondary flash to main flash, doing a reversion if necessary, and reporting the process back. On the cannot side, so as I mentioned, this is a standard API client library for all applications that require CAN access. It abstracts the applications from the underlying hardware and software architecture, so it is fully portable. It's certificate-based authentication to make sure that that CAN access, when it's granted, has the most secure envelope possible. And finally, it has policy-based bandwidth allocation and ECU source address restrictions to further enhance the security. So what's the current status? As I mentioned, the CAN translator service, that is in series production today. So it's feature complete and the production source code is released. There is another component with the CAN security manager or CAN access manager. This is not yet in full production. We do have an alpha phase software released. We have partial functionality in the code there. And we do have the backlog to do the authentication mechanism. That's the next part we'll be working on to add to this stack. The software update use service. So as I mentioned, we did do a proof of concept with the Conto update manager. And the reason we chose Conto is because it's the only update manager really designed to work across multiple domains. So it could be at the container domain, the OS domain, or an embedded ECU AutoSAR type of domain. We're in the process of doing the use service discovery and defining how that should operate and what the features will be. It's a topic of discussion in the U protocol weekly meetings and the software orchestration group that meets every couple of weeks as well. And we plan to have an initial spec ready at the end of Q1 next year for public consumption. So that's my last slide. What questions do people have?
From the audience. Well, I have a question, which is, so you mentioned that Canode is going to be going into production or is already in production. So what sort of safety certification? I know security is your main issue, but what about any safety certification that you might have had?
Right. So because we have domain separation, all of our safety critical functions are in the ECU.
Okay.
And we specifically make sure that none of those features are in the high performance compute. So that's the way we take care of it, is separation of concerns by separation of domains. I will say that we're working on a way to have some more safety critical type functions move into the high performance compute, and we're evaluating ways to do that, but it's too early to talk about the specifics of that.
Okay. Yeah, that makes sense.
Thank you, Carton. I was wondering, do you have any feedback or experience with OEMs opening up or agreeing to the idea of standardizing access to their CAN subsystem? I guess they are pretty much in control of the CAN access, and they want to remain in control there. So did you talk to some of them already about this idea, and what do they think about that?
Yes, so talked to several OEMs, and it's interesting. I think part of the teams we talked to, they dread having the discussions with their cybersecurity teams because they're always tough discussions. So part of it is coming up with the business justification of why this is needed. But that's what we had to do internally as well. Like that's a problem that everyone has to go through. I think probably the bigger concern, though, is making changes to their architecture that's already in production and is already functioning. So it's investing in code that's already functional and meets their internal requirements and justifying the additional development to do that. So I think that's why it's so critical to have an open source reference implementation to show that you don't have to develop this on your own, or if it's a tier one supplier doing it for you, they don't have to start out on their own. There's a model that you can use, it is functional, and it makes it a lot faster and easier to adopt. So we are talking about proof of concept integrations with several of our OEM partners to explore this, to and that's generally how it happens for things to make it through series production a few years later. So no agreement at this point for it to be into production, but we're going down that path to show that it's likely feasible.
Thank you.
Maybe the same question. What's the next thing you guys need from the U-Protocol project?
Yeah, so we been talking to Kai quite a bit, actually, and Stephen as well. We need help figuring out how to do the U-service definitions and how to make sure we categorize the different functions properly, and then to move that to become a standard once that's done. So we need help developing the standard, and then we're going to be implementing a proof of concept with our own update mechanism. So really getting that to maturity. We know the capabilities there, and it's been talked about before. It's really just being deliberate about moving it to series production and understanding what a production type solution would be.
So UP-CPP, UP transport, MQTT CPP, and a few other things we talked about. Yeah, that's not my question. Yeah, so there were two large projects that GM contributed, was U-Protocol and U-Services. U-Services was a definition or a framework for defining abstract service-oriented definitions of vehicle services, cloud services, all kinds of services. And it's basic functionality of defining what the service is and how that service would talk to applications and so on. It's rather than VSS, which is at a signal level, U-Services was at a service level. And so it provides a means of allowing two different automotive applications running anywhere to talk to each other using RPC, pub/sub, notification patterns, versus just set and get of a signal, which is VSS. But I have a question for you. Could you go back to the slide where you had a picture with the container and then the different ECUs?
Is it this one?
No, there was another one that you had.
This one?
Yeah. Oh, actually, you can go back to the other one. It's fine, but it's to the same. So the question I have is on the OCI container environment, your CAN access manager is this container environment, you're planning to deploy one of those per ECU that it would talk to? So, because I'm wondering, the CAN access manager, do you plan to have like application A talking to ECU 1 and application B talking to ECU 2 with only one container, or do you envision deploying containers tightly coupled to ECUs?
Yeah, that's a great question. So it really depends. So what's interesting here with this architecture is if you look at the CAN library itself, and as we add capabilities to that with the CAN server and the CAN access manager, this becomes the single largest resource user on a telematics device. So it uses more RAM and more CPU basically than all the other containerized applications put together. So it's essential that that be one central server and one container that all applications can access. And then as far as the containers themselves, we see as many containers as necessary because we don't have any additional overhead with having applications broken into additional containers. So we have a very lightweight Alpine Linux base image that I think uses 12 megabytes of RAM. And that same base image is used for all the containers. So there's no incremental RAM utilization as long as the same base image is there. So for security reasons, we separate them into multiple containers, but there's no, we can tailor the access, but there's no real overhead for doing that.
The reason I ask is because you could do something at a lower layer, right, at like a Linux layer or others with access controls if you're doing container to ECU. And but if you're putting all these different applications into a single container, then you need to manage it within that container because you have to. So I'm just wondering, it might be simpler if you're going to split it up into multiple containers, and each container is access control to do it at a Linux level using some other method.
Yeah, we did look into that and actually had a lot of push for that at the beginning. It becomes more of a, I guess, a bespoke implementation as that happens, because we're not really abstracting away from OS configurations or other configurations. It's still a possibility that a partner could do that. As long as it's transparent to the application, it doesn't really matter. But we were moving that up a level to abstract and manage it separately.
Might be easier for those tough conversations with the cyber folks of the different OEMs. But anyway,
Good point.
because I've had those conversations with them at our own company.
Thanks. It was really interesting talk. What I would like to learn from you, what's your experience with kind of quality control you have established when you're using now these open source components in security relevant applications? How do you ensure if the updates in these components that it's still according to the spec, which kind of quality assurance you have implemented, and is there a way to share the cost of that so that somehow you have some kind of a quality assurance label on it so that not everyone who is using it has to do the same effort?
Yeah, let me give you a little more perspective. I'll pull up one of the architecture diagrams that shows where we are today. So, yeah, if we look here, you see there's this tier 1 high performance compute. So this is the Linux telematics device that we built. Well, we didn't build the hardware, but we built the entire software architecture on top of it. And it mounts on top of our embedded ECU on our engine itself. So it goes out with every product we ship. We designed our own assembly of open source components, some Eclipse, some not. We started this development in 2019. And we basically we did it all ourselves. We picked all the open source components, some from commercial vendors that were supported, some we designed on our own that we later released to open source. And as we're going to production, you're right, it was quite a challenge to get everything certified and to show we had an update path there. We also realized that's why, we need to take a more of a standard approach for the architecture. So we had a development timeline we had to hit. We did the best we could for picking solutions that worked, but they're not necessarily scalable from a broad support and long-term support perspective. So I think it's an iterative approach to, first you learn on your first device of how to pick the solution stack and try to meet the requirements. And then as that matures, you look at how do you replace the problematic components with more secure or more open versions of that.